All right, so today I said I would announce what we're going to talk about, and I decided I'd talk about machine learning today. We're going to cover all the forensic stuff, but there's a couple extra weeks here beyond what we need to cover the forensic stuff, and I'm adding an extra period like Velociraptor. But today I'd like to talk about machine learning. And I've got a few. Now, machine learning is so important. AI is everywhere. Everybody is totally freaking out about it. So I think it's important to learn for every possible field. And I think people should, it's a very good idea to learn how it actually works, because it is not what people think it is. What most people think of is large language models, and they think that it understands English because it can now pass the Turing test. It can talk to you like ChatGPT as if it was a human, but it doesn't understand what it's saying.
Have you used your M1 to do a machine learning?
Well, only indirectly. I mean, you're connecting to cloud services that are doing it.
No, your M1 is AIPC.
Is what?
It's AIPC. You can do the...
Sure, you can. Yeah, you can do some of this stuff locally, but I haven't done it. I'm using cloud services, but yeah, you can run these things locally, the smaller ones. Anyway.
No, your M1 has NPU, neural processor.
That's interesting. I didn't know that.
CPU and NPU.
It has a GPU, yeah.
No, it has NPU also.
NPU, okay. Well, I didn't know that.
It's for doing PI.
Yeah, well, that's interesting. But I'm not aware of any AI models particularly to run on the M1. But anyway, let me. I'm just going to download these things. Thought I had them, but I don't. All right, that, and that, and that. All right. So let me talk about how AI works. And I'm going to find where this is. It's going to be in my downloads folder. All right. All right, so this is what I wanted to do. Start this. So these are the types of machine learning that exist out there: supervised versus unsupervised, online versus batch, and a few other things as we go ahead. So machine learning is it is a computer that learns how to do something without being programmed how to do it. So, for example, if you have a spam filter, which we've had in all our interview animals for a long time, the old-fashioned way to make a spam filter is a human would have to list all the words. I think I got that down here. Yeah, here's traditional programming. You'd read spam and you'd find words like for you and free and amazing and other patterns in the name or body, and then you write an algorithm to look for those things. And if a spam contained a certain number of those, you'd call it spam and throw it away. This is the old technique. The problem is the bad guys immediately figure this out and then they misspell the words or something, and now you're getting through the filter. So the machine learning solution is like this. That's traditional programming. You study the problem, you write rules, you evaluate them, then you launch your thing, and then you analyze the errors and try to improve it. In machine learning, you study the problem, you design an AI model, which is a series of neurons that can just learn from experience. Then you train the model on some training data, which is probably in this case labeled spam or not spam. Then you evaluate to see how good it is. You analyze the errors to see if it's good enough, and when you think it's good enough, then you launch it. And you can have it continue to learn as it runs forward. So that's the modern solution. That's machine learning. All right. So, and the interesting thing here is no human wrote the algorithm, and that means no human understands what it's doing. So if it makes a mistake, like there's some emails it marks as spam that are not spam, you can't find out why. You can't tell it to quit doing that easily because you can't figure out what part of it made that decision. That's why there's another field developing called explainable AI, which would explain why it works, but that's in its infancy. So you can train it periodically so it keeps on getting updated as spam comes in. And so there are other cases besides that we might want. There's some problems where there is no known algorithm. Nobody knows how to do it, so sometimes a machine can learn how to do it anyway. Things like speech recognition. Ever since the 1960s, we pretended we're going to have things that can understand you when you talk, recognize your voice. They've only started coming out recently because they use machine learning. All right, and then there's trying to help work together with humans, which is the way it's all really done. So you study the problem, you make a machine learning model, then you inspect it and gain a better understanding of the problem. This is essentially what really happens. Machine learning models do not learn much by themselves. They require constant adjustment and tweaking by humans that understand how to build them. All right, so it's good for problems where the existing solutions are very difficult, or complex problems with no good solution, or fluctuating environments where they have to keep moving with the trend, and so on, and also analyzing large amounts of data. Doing things like, say, reading all the social media posts and then rating whether people are positive or negative this week, that kind of thing, is the kind of job AIs are good for. Also summarizing large things like whole movies, whole books. All right, so let me go check for comments in the online system. All right, yeah, Bill Gates keep getting rich too, yeah? All right, so you can analyze products on a production line to classify them. If you have two different products available, you can do image classification, use these kind of things. You can detect tumors in brain scans. And AI models are now better than doctors at reading MRIs. You can classify news articles. Like I said, you can read them and classify them into categories. This is natural language processing. Now, it doesn't do it by understanding what the words mean. It just does it by finding mathematical patterns in the words. All right. But the main things used here are transformers. These are what made the large language models possible. And transformers take English sentences and turn them into a list of numbers. They have a high dimensional space, like 1,000,000 dimensions, and they assign 1,000,000 dimension coordinates to every word, essentially. And so there's vectors for each word, and they have patterns to them. So they've arranged it so that the meaning is encoded in the location in this vast space. That's what transformers do, and they turn out to be very successful at predicting the next word in a sequence, and therefore making paragraphs and pages of text that look pretty much like a human wrote them. But it does all this without having any idea what any of it means. So you can make a chatbot like we have. You can forecast your revenue, voice commands. Detecting credit card fraud is a big one. This is a really good job for machine learning, is finding unusual objects in a complicated system, like the fraudulent ones. So finding the credit card transactions that are suspicious is a good task here. And the same thing, segmenting clients based on their purchases. If you're running something like Netflix and you have all these customers and you'd like to sort them into categories to figure out, these people I should recommend this, those people I should recommend that, these people are bots and I should kick them off, these people are criminals and they're trying to steal my service. You want to sort your people into categories. All right. So here's how. There's various ways to divide machine learning systems into categories. One is whether they're supervised during training. Supervised training means humans have to label the data. Unsupervised training, humans don't have to label the data, so it's much cheaper. So that's supervised and unsupervised, and there's some sort of halfway in between things. Then you can either have them online or batch learning. This is real well known in large language models. Up until about 6 months ago, all the large language models only knew about the internet until 2021, because there was one pile of data called, I think, the pile, which they prepared by scraping basically the whole internet up to 2021, and they all learned on that data. So they learned English structure and other languages from that, but they didn't know anything happened after 2021. Then, recently, a few of them have begun to connect online so they can see modern data on the web. Now, this has been difficult to do because once you do that, several really bad things happen. One of them is people can now poison your model by putting junk on the web that will train your model to do bad things. And a more subtle problem is that most of the web is now AI generated. Something like 60% of the content on the web is produced by earlier generations of AI. And studies have shown, just as you might imagine, that if you train an AI on text that was written by an AI, you get garbage. That magnifies the errors. And that's what happens if you connect it to the modern internet. So that's why this has been kind of an issue. Anyway, all right. So the different supervision categories are interesting. Supervised learning is the simplest, most obvious one. Your training data has labels. Like you have, these messages are marked spam, these messages are marked not spam, and you have some large number of both of them. Now model can train to categorize them based on that. The problem is you had to pay humans to separate these, or somehow get humans to do all this work into labeling them into spam and not spam. But that's the supervision. So classifying, like a spam filter, is fine. Also regression, you have measurements of something, and then you're trying to have a new instance, you're trying to predict what its value will be. example in the projects where you try to predict the price of a house in California based on a bunch of information, like the latitude, longitude, average income in that area, and so on. So in unsupervised learning, though, you have something like a bunch of pictures you found on the internet, and you don't want to just do something with this even though they're not labeled. So what you can do is you can categorize them. You can sort them into categories. Here's a group that belong together, here's a group that belong together. So you can sort of do that even though they are not labeled. You can sort them into groups, and then you can visualize the groups to understand what you've got, and you can then deal with another issue. Here's dimensionality reduction is a big issue, and this is true of your brain. I used to do brain research. Your eyes are very sensitive. They see a lot of basically pixels of all this data and all this motion. There's far too much information there. If you had to process all that information, you would be paralyzed. You'd be unable to move. It'd take you a long time to decide whether you can step forward without ramming into the wall, because the number of pixels required to make that decision. And yet, your brain is extremely good at this. If something is flying at your head like a baseball, your head will jerk out of the way. It takes about 1/10 of a second to make that calculation. So your brain is designed to figure out what the important information is and focus on that and ignore the unimportant information. This is done by, I think, the amygdala. This is super important. You have to do this. If you had to process every pixel, you could never respond to anything in any reasonable amount of time because your processing is not that fast. And it's exactly the same thing with machine learning systems. If you think about a Tesla has a high-resolution camera in the front, and it has other cameras on the side. It has like microphones to pick up sound. It's got a lot of information, way too much information. It can't process all that information. It has to pick the important information out and throw away the rest. And this is called dimensionality reduction. You have to somehow combine all the data coming in into a small number of summary pieces of data that you can use to determine what's important, like, am I about to hit something? All right, and that's a task of categorizing things. It's called feature extraction. You can take data and you can decide what are the most important parts of this data, and that's an unsupervised learning job. And then you can do anomaly detection. Like I say, unusual credit card transactions. You have some kind of measurement, like the location and the amount and the time of the transaction and the previous history of this customer. There's information that you can graph somehow, and you can now say, these are all clustered together, that's normal, this one is not normal, so that's probably the fraudulent one. That's the kind of thing you can do. All right, and you can discover attributes, relationships between attributes. When the loyalty cards came out, for Safeway, I was running databases then at a company. I was very interested. You know, if I had that data, I could do so much. The first thing I thought is I could arrange that none of the food will spoil. I could make sure to buy just the right amount of perishable items because I know the customers, I know how much they're buying. I could predict how much they're going to buy and buy the right amount. But they went much further than that. And one thing they found with this is 7-Eleven found that if you want to sell more beer, you want to put it by the diapers. And this might not be obvious, but what happens is nobody would buy diapers at 7-Eleven. You normally buy them at grocery store because they're cheaper. If you're buying them at 7-Eleven, that means you ran out of them at home and it's night. And now the wife sends the husband out to buy diapers. And he says, well, I'm here, I'll get some beer. That's why these two items, you wouldn't have guessed this, but it's true. And I know Target similarly had this problem. One of the big chains, they found out that they were able to predict when women were pregnant by watching what they buy. They were so good at it that they started sending catalogs to women who are pregnant, because this is real important to advertisers. Advertisers have learned this. Most people never change what they do. They have the same brand of toothpaste, the same crackers, the same breakfast cereal forever for no good reason. The other ones are just as good, but they like one and they stick to this one. And there's only a few times in your life when you are actually willing to change anything. And one of these is when you have your first child. It throws your whole life into turmoil. Now you can convince them to buy a different brand of toothpaste. This is the super important time for an advertiser to get to them. Your only chance to get that customer. So that's real important. So they would send them special catalogs to the pregnant women, and it would be mostly full of like baby stuff and clothing, and then also have other items they're trying to sell. And they got in trouble because it was extremely obvious when this catalog came in the mail that the woman in the house was pregnant. And they'd have fathers coming in, you sent this, my daughter's a good girl, she can't be pregnant. And she was, but she didn't tell her father, but Target knew. So they realized they were getting in trouble for knowing too much, and they had to change that thing to also add like some tractors and chainsaws to that brochure. So it was not quite as obvious that they knew. But that's the thing. Analyzing data, you can discover trends in the data that tell you things that are not obvious. Anyway, So then there's semi-supervised learning, and in a whole machine learning class, we got a fun project where you do this. You first just group the objects into groups, then you find examples in the center of each group, and then you make humans label them. So the humans only have to label a few objects near the center of each group, and now you can identify the whole groups. So this is kind of a clever way to use the minimum amount of human effort to create learning. And then here's another one. This is how those image generators work. You've seen these image generators like Stable Diffusion, where you can say, show me a cat riding a bicycle in the style of Picasso, and it will do it. And the way they did it was they took a bunch of real images of all the different artists, without getting permission, by the way, for which they're being sued. And then they took these images and they added a little snow to them, a little more snow, until they made 1,000 gradually more and more blurry images to where it's just snow. And they trained the model how to remove the blur. So, and then to make the one you want, they will just feed in noise and remove the blur from the noise, and they'll end up with something like what you described. So this is, you create data, which you can then train it on. And I never would have thought that was possible. I never would have thought it was affordable. But they're so cheap, they offer that service for free now. And all the chatbots can generate things that way. And here's an example too. If you go to I've seen ads for modern phones. You can take a picture of something at like a concert, and you can say, oh, this guy's head is in the way, remove them, and it will fill in the background as if you had a picture of what was behind that guy's head, like this. And this is how you do it. You take a real picture, you cut out a piece, and you make it practice filling in the piece because you know what the right answer is. So you can make a machine learning model that can guess what would look good to put behind that. It, of course, doesn't know what was really there, but it can make it close to what would really be there in a natural scene. So, all right, then there's reinforcement learning, where you train it like to play a game, where a human or somebody tells it whether you won or lost, and then you try again. So that'd be, here you have a robot, and it can either go to the fire, which is bad, or to the water, which is not bad. If it goes here, it gets punished. That was a bad move, so it learns don't do that again. And that's the general thing. This is how they learn to play games, like chess and such. So I've got some Kahoots. Might as well try them. All right, here. I figure out how to start it. Why is there no start button? Am I missing something? There's supposed to be a start button. That's what I thought. That one shows the pictures. Where is the start button? I am logged in. Assign to participants. Host. Starting live Kahoot. Oh, they've changed it. Okay. Well, I hate it when people change things. Change the start button to host, just to irritate me. What's that?
You got the
One. Oh, I did. I thank you for telling me. Good. All right. Good. Let me start the right one with the new altered hidden start button, just to bother me. Everybody in tech has ADHD. They just constantly change things for no apparent reason. All right, so what part of the system learns and makes predictions? That's the model. You have a bunch of simulated neurons, and the neurons have a bunch of parameters, and you train it, it adjusts those parameters, usually billions of them, until it runs, and then you can predict predictions based on what it has learned. All right, what system would mask part of a training image to generate a labeled data set? That's self-supervised. No human had to label the data. It automatically created training sets where it knows the right answer. All right, what system needs labeled data? That's supervised. Somebody had to put in the work of labeling that data. That makes it more expensive and harder to find that data. This is why, for example, Facebook, I don't know if they're still doing it, Facebook or Instagram for years, was getting people to tell you who all the other people are in your photo. So they can go label all their instances of the same face. They're trying to get their users to provide the labels they need. All right, and which one learns how to play based on rewards and penalties? That's reinforcement. With fake names, you'll have to tell me who they are if they want their points, but Amber looks like it might be a real name. The rest of these, not so much. Anyway, all right, so you can have batch learning where it just has a pile of data and learns all at once, and that's it, and typically trained offline, and this is how large language models were until recently, and therefore the performance will decay because their data they were trained on gets more and more out of date as time passes. That's called model rot or data drift. Similar phenomenon on my web pages. My older classes, I had a bunch of links at the bottom, and people will complain those links don't work because they go to other sites, and those other sites change and go down about 10% per year. Then there's online learning, where you just keep feeding it new data, fresh data all the time, so it can learn from rapidly changing data. If it learns quickly, then it will forget the old data quickly. So it will be like trendy. It'll be like always doing the new thing but not remembering the old thing. A low learning rate has more inertia, so it'll be more stable but less quick to respond to new things. Those are your choices. All right, so then you can ask questions about how good your model is. How well does it generalize? If you give it new data, can it do the job? Like you can train it to tell dogs from cats, so then to see how good it is, you'll show it new pictures it's never seen before and have it try to sort them into dogs and cats and see how well it does. Now, instance-based learning, it learns the training data, it just memorizes the training data, and then it calculates the distance. A new instance, it says, well, I'm close to these green ones, more green ones are nearby than a yellow one, so I'll call this one green. That's one way to do it. Take a measure of similarity just to see how close the new input is to the known ones. But model-based learning is what the modern systems almost all use. It makes a mathematical model. It learns, I'm going to draw a border, and everything on this side of the border is green, and on this side of the border is yellow. That's the model. So it has made a mathematical description of the situation that will cover all instances, not just the ones it's really observed. All right. So you can take money and happiness. Does money make you happy? Well, they can take happiness and measure it against GDP for a few countries, and when you graph it, you see a nice positive trend. So it looks like you can just put a straight line through here, and pretty much money makes you happier. So that's fine. You can make a linear model with just one attribute. And so you'd have parameters, theta 0 and theta 1 is the slope and intercept of this line. So you can try various values, and you can pick the best line through the curve. And there's a line that looks like a pretty good fit to the curve right there. So that's one kind of prediction. Now, to select that best line, you need a performance measure. And this is what I actually started doing 50 years ago, the first computer task I ever did. The classic solution is to take the distance between the point and the line and square it and add the sum of the squares. So being too low is just as bad as being too high. That's a famous, then the mathematics gets very easy, and it's very easy to calculate what the best line is. All right, so that's one way to do it. You have to have a cost function, and you minimize the cost, then you found the best model. So there are some challenges. The main challenge is you can't find enough good training data. That's why people say in the future, companies that have access to a lot of data are going to make a lot of money. And that's why the artists are suing who had their art used to train models without their permission. The New York Times is suing AI models, saying you shouldn't have trained your model on New York Times data without paying for it. And companies that have a lot of data, like Facebook and Twitter, are imagining they can make a lot of money from that data. We'll see, but that's a problem. Or you get poor quality or data that's not accurate enough. And then there's overfitting and underfitting, which is a big problem. Even if you have enough data, how exactly do you figure out how to get the meaningful trend in the data, but not model the noise in the data? So if you don't have enough data, then you have a low quality model. If you have a lot of data, it doesn't really matter which model you use. This is general factor machine learning. Almost any model will optimize if you have enough training data. Now, another problem is non-representative training data. Here's that graph of happiness versus GDP. And we fit this data, these blue dots, but there were these other countries out here which we didn't include. And when you include them, you see this straight line is not really a fair representative at all. It's not true at all that if you make a little more money, you'll be really happy. You can have a lot more money and you seem not any happier at all. You can have a lot less money and you're not this miserable. So the real, if there is a trend here, maybe the best representation of this data is that it has nothing to do with money and it's just always the same. That might be a better description of the situation, and that's the problem if your data is limited. And this is what keeps happening in the stock market, and it's now happening with AI. Every time there is a new thing, all the stock starts going up using the new thing, and everybody says, oh, just put web in your company name in 1992 and your stock will go up. Just put AI in your name right now and your stock will go up because it's going up. But that doesn't mean it's going to keep going up. It's going to hit some kind of ceiling and come down, and from the part that's rising, you can't really predict when that turnaround is going to happen. So that's poor quality data. So you spend a lot of time trying to fix data. This is always a problem. Some of your customers don't answer the questions, and so on. You might have irrelevant features. So you have to select what features seem to be important, perhaps combine available features to extract it. Create new features by gathering new data. These are all things you have to do where humans are feeding in a lot of judgment calls to get the answer. If for something like predicting who's going to win the election from a poll, it's very much like this. You survey a bunch of people, and then you have to correct for things like, did I really have the right number of people in different income categories, different races, different physical locations? You have to correct for that. What about people that lie on the poll? What about, how did I do it? Did I only call people on landline telephones? Then I'm not really finding a bunch of people. It's a problem. You have some data, but how good is your data? And how do you correct for the systematic flaws in your data? This requires human judgment. Right, and then there's overfitting, and this is what happened to Donald Trump. I don't know if you remember, but when COVID first started, at one point Trump said, it's not in this country at all. Then he said there's only 4 cases. Then he said there's only 12 cases, and what's going to happen is it's going to vanish by Easter. It's going to be gone completely, which was a very strange thing to say. And you wondered why he said that. The reason he said that is because one of the people on his staff was an economist, and he knew how to use Microsoft Excel, and he fed in the data. And if you take, I used to do exactly this 50 years ago. When you fit, now there's a mathematical model to put a straight line through data. You can also fit any polynomial through data. But if you do fit a high-order polynomial through your data, this is the kind of fit you get. So here is data, which I think is that happiness again. So here's the data. So if you fit like a fourth order polynomial, it will do this. It will wave through the data points, and then where there isn't much data, it will do extreme things like this. This is a mathematical fit, a best fit to that data. This is what I call overfitting. You are clearly not really representing the real trend here. But from a mathematical point of view, it's hitting the points very accurately. So it's making the loss small, but it is fitting the errors and the noise in the data. It's not fitting the trend in the data. And this is what happens when you fit too high a polynomial. And this is what happened to Donald Trump. They took the COVID cases for time, and somebody put it in Excel and fit a higher order polynomial, and it did this. It went to 0, like a month in the future. He said, it's going to just go to 0, like magic. It really did that in a prediction, because they didn't know what they were doing, and they accepted this kind of prediction. But the mathematics will do this, and that's called overfitting, and that's a big problem. And it is proven about 3 months ago that the large language models currently in use have overfit the data, because authors have wondered, did they train this on my novel? So they would ask it like a question about the novel. They would feed in like a page of the novel, and it would reply with like many more pages completely straight from the novel. So it was just totally memorizing that novel, which is like this, going through all the points exactly, instead of just going smoothly through the average of the points. This is a consequence of overfitting. So there's hyperparameter smooths the data. And so you choose a smoothing parameter to make it accept a less accurate fit of the data, but hopefully less following the noise and more following the trend, which is, again, just kind of a human concept that you're feeding in. Nowhere in the mathematics, nowhere in the data, but humans have some idea that this is catching this one is accurately representing the data, and this one is not. Now, I do not have any proof of that. How do I know it doesn't do this? I just have an intuitive feeling that the smooth curve is more likely to be right. But if I don't have any measurements here, how do I know it might do that? That's why it's got an artistic feature. It's not as simple as a science. It's got basically artistic thinking involved in there too, human putting in intuition. So then there's underfitting. Of course, if your model is too simple, like you're putting a straight line through something that is curved, then you'll never get a good fit either. So it's a part of the job to regularize enough to get a good fit, not too much and not too little. So machine learning is making machines better at this. There's many types of them. And so you need a training set. And typically you're doing model-based, where it tunes parameters to fit the model. All right. And so you split your data in a training set and testing set. You take typically 80% of the data and train the model, and you keep 20% back to test it later to see how accurate it is. All right. And you can have, another problem is you often have different data. So you might train a phone app to recognize flowers from photos, but you download flower photos from the web, and those are not going to be equal to people taking photographs of flowers. And of course, that's what you want. I've seen these. You can take a picture of a plant, and it will tell you what the plant is, but the pictures on the web are not equal to that. So that's a problem. And this happened to the first generation of medical bots. They tried to train an AI to tell people that had whether they had cancer or not from like a lung x-ray. But when they trained them, the people who didn't have cancer just had a picture of the lungs. The people that did have cancer were patients, and they had a little square in the corner, which was the patient's name and serial number and patient number or something. So the model just looked for that square in the corner. These are the guys that have cancer, because it just solved the problem using whatever data is there. You have to watch out for that. And all right, so let's try another Kahoot, and that's all I'm going to do in the way of lecture. I just want to demonstrate a project after this. So host. Fine, host. I will host a Kahoot. All right, so which system will memorize each image and then compare test systems to see how similar they are to them? Test images, I guess that should say. That's the instance-based one. By the way, this reminds me of something that came up in politics about 6 months ago. They were interviewing people, Ketanji Brown Jackson, they were interviewing her for the Supreme Court. And they said, can you tell us what a woman is? And you think you know, but then there's the medical cases. And she said, I don't know, I can't do that. And they would say, oh, can't you do that? Anybody can do that. Well, it's not so simple, Maybe sometimes it's simple, but there's cases where it's not simple. It's instant-based. You could define like a woman and a man and then say, how close are you to this or that? But it's not a perfect process. Anyway, so which system is best if you want to stay up to date with changing data? Online, of course, feeding in new data as it comes in. All right, and a number that increases as the model gets better. The utility function is biggest when you have a good fit. The cost function is lowest when you have a good fit. All right. All right, and which of these will lower generalization error? Hyperparameters are the smoothing factors that prevent overfitting by forcing it not to make the best fit to the data, but a smoother fit for the data, so it will more likely catch the trend, and therefore when you test it with the test data, it'll be a better fit. That's generalization. So the hyperparameters do that. All right. And we're good. All right. PW might be initials. Majority might be able to figure it out, although more of a name would be good if you want to make sure you get your points. All right. Now I just want to demonstrate the first project, but it's about 10 minutes to 7. I'll take a 10-minute break, and then I'm going to demonstrate the project, which you can do for extra credit. You'll find all this stuff on the class. Here it is. So that's down here in machine learning, this ML100. You can do this for extra credit if you like, and I'll demonstrate it. I think I'll probably also talk about these OWASP things a bit. They're very interesting too. But that's what I'm going to do, but I'll do it in 10 minutes, so I'll be back.
The machine,
yeah.
They picked up some, there's one outside IP who's trying to get into the WAN connection.
Oh, somebody hacked the firewall?
Somebody tried to get into WAN connection.
Yeah.
Using some management protocol.
Oh.
But the funny thing is the gate is picking up the data.
So you found that in the log?
Yeah.
Yeah, that's interesting. It might be an attacker. It might be the college administrators trying to do something.
But it's picking up the data from inside the room. So is something from inside the room trying to go out?
Yeah, I don't know. It's an interesting question. I did stop. Wait, I better stop.